Today we begin our lecture 18. We will continue discussing convolutional codes. Last time we spent almost the entire lecture talking about the Viterbi decoder. So, let me do the following. I will just run through the slides and then I will do a quick recap. So, we started by looking at by setting up the trellis of the convolutional code, and the way the convolutional code is set up is that you have all your every branch in the trellis is labeled with an output segment in such a way that from start to finish, that in going from start to the end node, every path that you take corresponds to a code word. You can identify the message sequence associated with that path by just looking at the sequence of reds and blues in this figure, and you can look at the code word just by looking at the output of the output symbols that are listed sequentially. So, for example, if you went along the top path, it would be a string of zeros like this and so on. And then we actually showed how you would use this for decoding in a particular example. So, in the particular example, here is the trellis and it is labeled just as we have shown it, and let us say that we took this particular message sequence 10111 000, and then the corresponding output sequence is over here. We introduced two errors as indicated by these red arrows, and this was then your received sequence. And then what we did was we went back to the trellis and we labeled the trellis by actually listing the Hamming distance between the output the segment of the code word corresponding to a branch and the segment corresponding to the received sequence. So, for example, here we put 2, 3 and so on. In this way we were able to label every branch, and then from a brute force point of view, all that you had to do was examine all paths from the start node to the end node and then pick the one that has the closest in Hamming distance to the received vector. But that involves too many computations because the number of paths increases exponentially with length of this depth of this trellis. So, the clever thing that the Viterbi decoder does is that it says, well, let us start from the left and keep going to the right, and you will see that in this way you can actually keep discarding certain paths, and that was the idea behind the decoder, and we pursued that and we were able to actually decode the message correctly in this particular case. Now, so with that, let me get on to today's lecture. Which is entitled Catastrophic Error Propagation. But I will just let me pull up some toolbars here. And put down a recap. Labeled the trellis diagram, and then explain the operation of the Viterbi decoder. So, that is what we did last time. So, today I just before I start our main topic, which is this catastrophic error propagation, what I would like to do is just make one point about last time's Viterbi trellis. So, let us just go back once to that. Now, if you look in the trellis, what I have actually done is I have put in 2 trailing zeros over here, and I have already explained in the last lecture that the reason for bringing them in, so that you could actually bring the trellis or the finite state machine underlying this trellis back to the all 0 state. So, that means the last 2 message symbols are actually known. So, even though the number of times you address the channel is 1, 2, 3, 4, 5, 6, 7, 8 in this instance, the number of message symbols that you are actually transmitting is only 6. So, these trailing zeros are a convenience and can also be shown to improve performance, but they do result in a loss in rate, and I thought I would just document that before continuing. Note by adding a string of zeros at the tail of the message sequence in order to bring the encoder back to the all 0 state. We have suffered a small loss in rate. How do you quantify that? If the convolutional code is rate 1 by n and has rate and has memory new. So memory new. So, what we actually mean is that this is the number of shift registers on the input line, then the loss in rate per message sequence of length n is given by n minus nu it is n minus nu by n into k by n So, it would be now the nominal rate of the convolutional code is 1 by n, but now the fact that you actually introduced these trailing zeros brings in this other factor. So, this is your actual rate, so that the loss in rate is this. Okay. As you can see, the loss in rate is negligible if n, capital N, is large. Now, I want to get into the topic of our lecture, which is catastrophic error propagation, and the way I will actually begin that is by using an example. In this example, consider a convolutional code So, this is an example of catastrophic error propagation. And we will abbreviate that to be CEP. So, consider the case when the polynomial generator matrix is given by 1 plus d and 1 plus d squared. And so, the input output relationship, as you know, is given by this equation. Okay. Now, so catastrophic, I am sure, has conveyed the meaning that something bad is going to happen. So, I am going to tell you what that is. Suppose your input, the input u of t. Now, of course, this is the input power series. So, this is the sum u k d to the k goes from 0 to infinity. Suppose the input sequence u sub k is such that this is equal to 1 upon 1 plus d, which would correspond to a continuous. So, this is equivalent to saying that your sequence u k goes from 0 to infinity is a string of ones going off to infinity. In this case, so now what I am going to do is I am going to go into this equation and I am going to plug in 1 upon 1 plus d for u of t. Then V1 of d, V2 of d is given by 1 upon 1 plus d into 1 plus d into 1 plus d squared, and that is the same as 1 plus d upon 1 plus d, 1 plus d squared upon 1 plus d. So, this is 1, and so the question is, what do you get when you divide 1 plus d squared by 1 plus d? Okay. So, let us do that as a side calculation. So, this is an aside. So, we want to determine what is 1 plus d squared upon 1 plus d. So, we will put down d squared plus 1 and d plus 1, and so it is important to remember that we are dividing, sometimes we are dividing power series and sometimes we are dividing polynomials. So, it is important to keep in mind which we are doing at any given instant of time. In this case we are actually dividing polynomials. Okay. So, we do not have terms going off to infinity, in which case what you do is whenever you write a term, you actually put the highest degree term first, which is what we are doing here. So, this is d squared plus d plus 1 plus 1 d plus 1. So, what we see is that this thing is precisely d plus 1. Okay, so, that was our little side calculation. Now, let us go back in here and say that, so now we know that this is 1 and this is 1 plus d. So, this is your V 1 of d and V 2 of d. Now, this is actually very bad, and you think you are looking at this and says, well, it is not clear to me, why is this very bad? Well, the reason for that is that here is an instance in which your input sequence was an infinite stream of ones, right. Your input sequence here was an infinite string of ones. On the other hand, when you come to your output is a pair of polynomials. So, what do the corresponding output sequences look like? This corresponds to the sequence V 1 of k, which is 1 followed by an infinite string of zeros. On the other hand, V 2 of k corresponds to 1 1 and then a string of zeros. So, even though your input has infinite Hamming weight, your output has finite Hamming weight. Well, why is that a problem? Because now supposing by chance the channel will to actually corrupt just 3 message symbols. Supposing the channel corrupts these bits. Okay. So, let me just write channel corrupted here. If these bits were channel corrupted, then the output sequence would look exactly like the output sequence corresponding to an infinite string of zeros. So, that means that a finite number of channel errors can cause an infinite number of message symbol errors, and that situation is called catastrophic error propagation. So, let me try to give you a definition for it. An encoder matrix G of D for a convolutional code is said to have catastrophic error propagation if there is some input u of t with infinite Hamming weight, generating, or rather that generates an output V1 of D, V2 of D, or in general let us say that it is a rate one by n convolutional code whose Hamming weight is finite. Okay. So, an encoder matrix for a convolutional code is said to have catastrophic error propagation. Now, I do want to emphasize that whether or not the right question to ask is whether your encoder is catastrophic or not. Sometimes people casually say that a certain convolutional code is catastrophic, but actually that is not the right terminology. For the same code you could have two different encoders, one of which could have catastrophic error propagation and one which does not. Okay, so that is why I have said an encoder is said to have catastrophic error propagation, okay, because this is really a phenomenon that has to do with the mapping between input and output. If there is a generator matrix G of D, as you see over here, which actually maps an infinite weight input such as this to finite Hamming weight outputs, then this encoder has catastrophic error propagation, and the reason for that is simply because a finite number of channel errors can cause an infinite number of message errors. This terminology stems from the observation that if the encoder has catastrophic error propagation, then a finite number of channel errors can cause an infinite number of message symbol errors. Okay. Now, obviously, this is a situation that you would like to avoid. So, the natural question is, well, what is it that is different between the two encoders? So, there are consider the following generator matrices. Okay. If you consider G of D, which was our older encoder corresponding to 1 plus D squared, 1 plus D squared, it turns out that this does not have catastrophic error propagation. On the other hand, if you look at the second polynomial generator matrix, which is 1 plus D squared, this has catastrophic error propagation. So, the question is, what is it that really is causing the trouble? And The problem is that in this second example down here, the two symbols in the generator matrix share a common factor, and that is really what is causing the problem. It turns out that there is no common factor here. So, now what I would like to do is state a theorem which actually tells you when precisely when catastrophic error propagation takes place. So, theorem: a necessary and sufficient condition on the generator matrix of a rate 1 by n convolutional code to avoid catastrophic error propagation is simply that the GCD of G1 of t, G2 of d, Gn of t is equal to d to the L for some L greater than or equal to 0. So, what exactly are these GIs? Well, these are nothing but components of the generator matrix. So, these things are the elements of the generator matrix. So, we will just put that in, where G of d is G1 of d, G2 of d, Gn of d. Is the polynomial generator matrix of the code. Okay. So, the theorem just says that all that you have to do is compute the greatest common divisor. If the greatest common divisor is some power of d, where that exponent is greater than or equal to 0. Of course, the convention is that if you take d to the 0, then that is 1. So, the GCD can be 1, it can be d, d squared and so on, but only these are permissible. If this is the GCD, then it does not have catastrophic error propagation. On the other hand, it does. Okay. So, for that, in order to dig a little deeper, I would like to go back and explain how GCDs are computed, because we will also run into GCDs when we actually deal with decoding algebraic codes such as the Reed-Solomon code. So, so just a quick review of computing the GCD. So, first of all, an example: what is the GCD of the integers 27 and 63? How would you compute it? Now, the algorithm that you would have learned perhaps in high school is that you keep dividing until you get remainder 0. So, 63 divided by 27, okay, well, so 63 divided by 27 is 2, 54, remainder is 9. then what you do is you go on to looking at 27 divided by the remainder, whatever is the remainder here. So, divided by 9. So, that of course, you know that the remainder is going to be 0. So, as soon as it hits 0, stop, and then you declare the previous remainder to be the GCD. So, in this case the GCD turns out to be given by 9. Now, it turns out that a similar algorithm will also work in our case, but we want to extract a little bit more information than this working actually gives us. So, what we will do is we will organize this computation in the form of a table. So, let us see how we do that. So, we will form a table in which you will have remainders on this side, then you have 63 and you have 27, and then you have quotients on this side. And let me draw some vertical lines. So, our first two entries are going to be 63 and 27 themselves, and I am going to put down a 1 and a 0 here, and a 0 and a 1 here. Now, the interpretation here is that 63 is 1 times 63 plus 0 times 27. 27 is 0 times 63 plus 1 times 27. So, you can think of this as somewhat very similar to working with an Excel spreadsheet where you have some formulae. Now, to compute the GCD, what we did was we kept on dividing and keeping note of the remainder. So, when you divide 63 by 27, the quotient is 2 and the remainder is 9. Now, this first entry in the third row I obtained in retrospect by taking 63 and subtracting twice 27 from it. So, the same thing over here, I take 1, subtract 2 times 0 and I will get 1. I take 0, subtract 2 times 1, I will get minus 2 over here. Now, the Excel type formula is still valid. 9 is 1 times 63 minus 2 times 27, because 63 minus 54 is 9. And now we continue. So, 27 divided by 9 gives you a quotient of 3 and a remainder of 0. Now, this 0 was obtained by subtracting 3 times 9 from 27. So, 0, so the entry here should be 0 minus 1 times 3, that is negative 3. This is 2 into 1 minus 2 into 3. So, that is 2 into 1 plus 2 into 3, that is 2 plus 6, which is 8. And you can verify that so let us see, excuse me, that should be a slight mistake here. So, what we want to do is we want to 2 into 1 plus 3 into 2, that is actually 8. So, that is fine. All right. So, now as soon as we got the remainder of 0, what we actually observed was that this is the GCD that we want, and the focus on this. So, what this table gives you apart from the GCD, because whatever calculations you did in the leftmost column were really of no consequence, are similar to what we did earlier. So, there is nothing new that the table adds. What the table does provide is this extra row that you actually see over here, and what this row actually tells you is that 9 is equal to this row actually tells you that 9 is equal to 63 times 1 plus minus 2 into 27, and it turns out that this expression will prove useful for us. Yep, there is just one small correction I want to make here. This thing here should actually be a 7. The reason being that like in an Excel spreadsheet, 27 minus 3 times 9 is 0, 0 minus 1 times 3 is minus 3, 1 minus of minus 2 times 3 is 1 plus 6, which is 7, and you can verify that this is correct because 7 times 27 minus 3 times 63 will actually give you 0. So, the extra piece of information that this table gives you is precisely this equation over here, and we will use that. Now, let us go on to by the way, in case you were curious, this table also gives you the ingredients that you need to actually prove that what you get is the GCD, because if you look down here, since when you divide 27 by 9 you get 0, that is telling you that 9 divides 27. But since 63 is a linear combination of 9 and 27, and 9 divides 9, 9 divides 27, so 9 also divides 63. So, this calculation here tells you that 9 divides both of the numbers on the top, and this would hold in general. Even if you had a longer table, this would still hold. This equation at the bottom is helpful because it tells you that not only is 9 a divisor of 63 and 27, it is also the largest possible divisor. Reason being that anything that divides 63 or 27 must divide 9 from this equation. Okay. So, this equation gives you, allows you to take that extra step and declare 9 to be the greatest common divisor. Now, let us look at the analog in the case of polynomials. So, let us do first of all take the example of the code that we had just done earlier, and what I am going to do is just cut this out. Okay. So, in this case, so apart from the remainder, we will also have two polynomials, d squared plus d plus 1, d squared plus 1, and our quotient. Okay, so why are these polynomials of interest? Because if we go back a few slides, you see that there were two polynomial generator matrices, and I mentioned without proof admittedly that whereas G1 of D is an example of an encoder which does not have catastrophic error propagation, whereas G2 of D does have catastrophic error propagation. And the difference really lies in that the GCD of the polynomials in the two matrices is different. So, what we are doing here is now trying to compute the GCD of the entries in first G1 of D. So, let us go down to that. So, we will list here d squared plus d plus 1 and then d squared plus 1. So, this is 1 0 0 1 just like in the earlier case. The next step is to actually divide d squared plus d plus 1 by d squared plus 1. The quotient is 1 and that is easy to see, and the remainder is d. Okay. And so, now in the next now the way we obtained this is multiplied this row by 1 and subtracted from this. So, we do the same thing for the remaining entries in the same row. So, here it is 1 minus 0 times 1, that is 1, 0 minus 1 times 1, that is 1. The next step is to actually divide d squared plus 1 by d. So, the quotient is d, the remainder is 1. So, we do the same. However, we got this entry, we will reproduce that procedure to get these two entries. So, we obtain this by taking this and subtracting d times d. So, here 0 plus 1 times d, that is d, this is 1 plus 1 times d, that is d plus 1. And finally, we divide d by 1. So, the quotient is d, remainder is 0. As soon as the remainder is 0, we can actually stop and declare this to be the GCD. So, this is then our GCD, and we see that the GCD is 1. Now, according to our theorem, which remains to be proven, as long as the GCD is some power of d, that L could be 0, then your code does not have catastrophic error propagation. So, that is the reason why this particular code does not have catastrophic error propagation. So, since the GCD of 1 plus d squared 1 plus d squared is equal to 1, there is no catastrophic error propagation by the theorem. Now, let us look at the second example, where g of d was 1 plus d and 1 plus d squared. We will set up the corresponding table. So, here is your remainder, and here is 1 plus d squared, 1 plus d. Actually, let us write the highest degree term first, so that the division seems more natural. So, d squared plus 1, d plus 1, 1, 0, 0, 0, 1, and then you are going to put down your quotient here. So, when you divide d squared plus 1 by d plus 1, the quotient will be d and the remainder will be d plus 1, and here it is 1 plus 0 times d, which is 1, 0 plus 1 times d, that is d. Now, you divide d plus 1 by d plus 1, the quotient is 1, the remainder is 0. So, we stop and declare that the GCD is d plus 1. So, in the case of this particular generator matrix, the GCD is not of the form d to the L, and hence by the theorem it has catastrophic error propagation. GCD is not equal to d to the L, L greater than 0, and hence this code has catastrophic error propagation. Okay. Now, I was actually intending to go through the proof of this theorem, but just keeping in mind that we have a fair number of topics to cover, what I am going to do is I am just going to give you verbally a sketch of the proof and leave it at that. Okay. So, we will not actually go through the process of writing it. The idea is that we have two other topics to cover, they are fairly major topics. So, I would like to be able to get to them. So, the way this proof actually works, let me zoom out here, is basically it says, so the equation to look at in trying to understand this is perhaps this one. Now, this was a particular example where the GCD was 1 plus d and the input was 1 upon 1 plus d. The general case is very similar. If the GCD is 1 plus some polynomial, the input can be 1 plus that polynomial, and you can prove that that is a valid input. And because this divides, the denominator divides both the entries, what you will get is outputs that are finite, are polynomials and hence have finite Hamming weight, whereas the input itself being of this form will always have infinite Hamming weight. You can prove that. So, that is why the greatest common divisor cannot be of the form 1 plus something, okay, because then you can play the same trick in that case to actually exhibit an output sequence that has finite Hamming weight even though input has infinite Hamming weight. Now, on the other hand, supposing the GCD is of the form d to the L, then you, by our extended Euclidean division algorithm, that is the algorithm we just carried out, you can actually show that a linear combination of these will give you a power of d. So, that means in turn, that means a linear combinations of the output will give you some delayed version of the input, which means that the outputs themselves must have infinite Hamming weight. Okay. So, I know I went through that rather fast, but presumably you can rewind and listen to it again. In any case, the idea was just to give you a quick overview so that we could move on. Okay. So, in a nutshell, a necessary and sufficient condition for an polynomial generator matrix to have catastrophic error propagation is that not have catastrophic error propagation is that the greatest common divisor of the components be of the form some power of d. And there is an analogous condition for the case when the convolutional code is of rate k by n for k other than 1, and we will come to that. Now, I want to get on to something else, which is now if you consider the way in which we have pursued convolutional codes, it has been a little bit different than our treatment of block codes, and intentionally so, because what we did was we followed a rather natural train of thought. I first showed you what a convolutional encoder was, what looked like, then I showed you why it belongs to a class of tree codes and is thus different from a block code. And then from that we went on to see that the finite state machine presents you with a nice description of the code, and this led to the trellis, and the trellis is of course extremely useful because you could do Viterbi decoding over the trellis. And now I just pointed out, by the way, when you actually select your polynomial generator matrices, you have to be careful to ensure that this phenomenon of catastrophic error propagation cannot take place. That is, you have to make sure that the components of your polynomial generator matrix are actually relatively prime, or at least the GCD is some power of d. Now, what we want to do is do something analogous to saying, you know, after all, performance in the case of a block code depended upon the minimum Hamming distance between a pair of distinct code words. So, isn't something like that also true here? And the answer is absolutely. Convolutional codes are very much like linear block codes, and they are exactly linear block codes when you actually terminate the trellis. So, how do you actually find the minimum distance of a convolutional code? Well, these are linear codes. So, finding the minimum distance of a convolutional code is exactly the same as finding the minimum Hamming weight of a non-zero code word. But the code, but it turns out that this is easiest done in terms of generating functions. So, that is what we are actually going to do next. So, I will begin, and I will continue this in the next lecture. I will begin by redrawing our finite state machine for the convolutional code. Okay, here is our finite state machine for our encoder, and let me just select the page, copy the page, move down to our current lecture and paste it again. Okay. So, now this is then our finite state machine description from earlier. What we want to do is to use this to enumerate all code words in the trellis. We want to use this to enumerate all code words in the trellis of infinite length, and it is not exactly the set of all code words, it turns out to be the set of all code words of interest, okay, but that is a minor subtle point. So, we want to do some enumeration, and we would like to make use of the finite state machine for that purpose. And we will use a generating function technique. So, I will just begin with a certain step, and then we will continue in the next class. Here we have outputs, the outputs associated with each of the transitions, and we know the inputs are either 0 or 1 depending upon the line is dotted or not. So, I am going to associate to the transition like this a term L, and with a term like this where the input is 1, the output is Hamming weight 2, I am going to associate L I d squared. Okay. So, the exponent of L tells me what the length of the sequence is, and the length of the sequence is always going to be 1. This is measured in terms of the number of input symbols. The exponent of I is how many information symbols were 1 during that. So, since this is a 1, that is I to the 1, here it was 0, so that was I to the 0, and then the exponent of d is the Hamming weight of the output. Since this term has Hamming weight 2, you have d squared over here. Since this is Hamming weight 0, you have d to the 0. Okay. So, with that we can now continue labeling the others. So, this is, all of them will have an L, this is I to the 0 and d squared, this is L d, this is L I d, this is also L I d, this one is L I. This one over here is L d, and I think we have labeled all of it in this way. So, now we are going to use generator function techniques to actually count all the paths that start from an all 0 state and go through and journey through this finite state machine and return to the all 0 state for the first time. Okay, we would like to enumerate those paths, and in terms of this trellis diagram here, what we are trying to do is we are trying to count the number of paths that originate from this start node and which end up at one of these all 0 nodes without revisiting it in between. So, paths of the kind that we are interested in, for example, is this path which goes down like this and merges with this, or a path like this which goes down like this, goes up, goes down and then merges like this. So, we are interested in all such paths, and we want to enumerate them in the sense that for each such path we want to keep track of not just the length of the path, but also the number of information symbols that were won along that path and the Hamming weight of the output, and that will turn out to be useful. Okay. So, I think we are almost out of time here. So, this just to recap, what we did today is we continued our discussion of convolutional codes, and after a short note having to do with loss and rate of a convolutional code with where there are trailing zeros, we talked about catastrophic error propagation. We wrote down a necessary and sufficient condition for a rate 1 by n convolutional code to avoid encoder to avoid catastrophic error propagation, and now we are beginning some enumeration of paths or code words, and we will continue that in the next class. Okay. So, thank you.